right, so if you remember yesterday we talked about some different features of functions, and a lot of this stuff came about before people had the technology tools to be able to graph a function and very quickly identify this stuff, and that is definitely one of the motivating factors behind the technologies, because we don't have to do this stuff by hand anymore. However, as it turns out, as soon as the technology takes care of basically just the graphing, these tools that we're talking about with derivatives and finding the maximum minimum are helpful for a lot of other cases because of the limits of technology. Okay? So, we talked about what a local max is, a local min, which is just sort of like king of his neighborhood or loser of his neighborhood. Anyway, and then the absolute max and absolute min, highest value in a region or lowest value. Then we talked about critical points, which were locations where the derivative is 0. We said that corresponds to a horizontal tangent line. Or when the derivative at a point doesn't exist. Those are critical points. And sort of an interesting phenomenon was that your local max, your local min occur at critical points. It could, when the function moves nice and smooth like that, we can definitely see that those tangent lines would end up, or the tangent line at that point is horizontal. I didn't have an example here, I probably should have, but if you have your function coming along and you have something like that, a sharp turn, clearly if we look at the tangent lines here, they're leading towards positive infinity, and tangent lines here are negative infinity, but so this is a vertical tangent line here, so f prime of c at this point right here does not exist, okay? But this point right here, that the tip of the tower, so to speak, is a relative max, or sorry, is a local max, okay? Anyway, another word that I will use like that accidentally from time to time is relative. Relative max, relative min, local max, local min, just depends on your textbook or whatever. So like I said, how do you find the local max and min without graphing? Let's look at the critical points. You can also look at endpoints. Find the derivative, set it equal to 0, and that normally would, that'll tell you where some possible local max and local min are. We'll talk today about a surefire way to guarantee how to get those. The other thing that we talked about was how do you find, and I put it on here, but I can't bring this back up, so I erase it. The absolute max and the absolute min using something called the candidates test. And that was find your candidates. That's all of your local max, min, and the endpoints. And then make a table, right? List all of those x values, plug it into the function, figure out who's the highest, who's the smallest, that's your winner, that's your loser. Maximum, that's your minimum. Y'all remember all this? Okay. So, we're going to kind of continue that sort of thought process. The title of this section is What Derivatives Tell Us. Okay? Derivatives actually can tell us lots of information about the original function. And so, there's, 6, 7 things that the derivative can tell us. If we're looking at the derivative, that can tell us where the original function is increasing, decreasing, where it's concave up, where it's concave down, where there's inflection points. It can tell us all sorts of phenomena. We're going to make a list of that. So what I want you to, consider is, I'm going to draw this one really big, and then we'll draw another one smaller. Let's just consider a cubic function that looks like this. That's y equals f of x. And I'm going to label some interesting points here. This happens to occur at A. This point right here is B. And somewhere in between them, put C. All right, then we'll go ahead and answer some questions on that function. So where is this function increasing? Ivan?
Just before A and after B.
Okay. So maybe we would kind of like trace along, it'd be it's increasing here and it's increasing here, right? So those are regions where it's increasing. Okay. James, where is this function decreasing then?
From A to C, and from C to B.
Yeah, we can actually probably say that whole entire region right there, yeah, it's decreasing right there. Okay. Where does this function have any relative max? Are there any local maximum, relative minimum, or relative maximum?
At A.
At A. What about relative min?
At B.
At B. Now let's think about that as it relates to the increasing and decreasing, which if I were to write this, where is function increasing, I guess we should do some interval notation. From negative infinity all the way up to A, as well as union B to infinity. It's decreasing on the region from A to B. So notice it goes from increasing to decreasing at A. And at A, there is a relative max. So that should tell us a relative max occurs when what?
When the function changes directions.
Okay. Utilize the words increasing and decreasing.
When the function shifts from increasing to decreasing and decreasing to
Right.
no,
Well,
it's
for relative
yeah,
max,
it's increasing to decreasing.
increasing, decreasing. So relative max occurs when the function, so f of x, goes from increasing to decreasing. I guess that's, when you think about it, that's kind of obvious. And that's true whether it's a smooth transition or an abrupt one like a sharp turn. Because it's increasing, 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 decreasing, decreasing, decreasing. You know, that transition point is going to be a relative max. Probably, would you agree with that statement? So we could also conclude that a relative min occurs when f of x goes from decreasing to increasing. Green work? Just barely. We'll just remain right there. Okay. Let's go ahead and draw some tangent lines here. And kind of see what's going on there. Now, there's a point where it kind of makes the most sense to transition from these tangent lines being on top of the function to having them below. Because like right here, clearly it would be below. Right here it would be below, right here it would be below. There seems to be some sort of transition point where the tangent lines go from being on top to being below. Does that make sense? Like I wouldn't draw it, this is kind of curving and going point up like that. The tangent line would not be on the outside, the tangent line would not be kind of on the left hand.
Right.
It's gonna be outside if you think about it, because the tangent line was, you've got this point, and you draw the secant line, you've got this point and this point, secant line. You bring this other point closer, and the actual tangent line looks something kind of like that. So I think we can all agree that the tangent lines are on the outside here. What's more, if you kind of think about it in terms of the tangent lines above or below, in this region over here, the tangent lines are all above the function. In this region over here, the tangent lines are all below. Okay? Now there's something that's kind of interesting about this portion right here versus this portion right here where the tangent lines are below. Well, how would you say?
The values are decreasing
The values
of the tangent.
Values of the tangent line are decreasing. That's a little more advanced than I was kind of expecting to say, but yes, that is true. I'm thinking more in terms of like, what does it kind of look like? It kind of looks like a cup, you know, kind of a smiley face right over here. It kind of looks like a frown right there. Okay, I'm kind of going. I should have specified. What does the graph look like? In terms of concavity, okay, we would say that this region over here is concave down, and this over here is concave up. Concave down, like a frown. Concave up, like a cup. Alright? So, today we are all concave up, because it's Friday. Except for you, Gracie. So, oh, okay, she's on that. I'm sorry.
I got the word.
Oh, okay. So, some things that we could say about the concavity. So it's the reason where it's concave up, the tangent lines okay, concave up, that's what you're here, are below the function. And where it's concave down, the tangent lines are above f of x. And this point right here, where it sort of like goes like, which you don't have to be all looking at me at the same time, okay? Where it kind of goes like, up, okay, up. Okay, I was kind of doing like an inflecting. It's called an inflection point. And it kind of, you know, have you ever heard like when you inflect something with your voice and you kind of like change the inflection or whatever, change the tone kind of. Anyway, that point where it changes concavity, which I've labeled C here, is called an inflection point. Okay? Now, I probably spent way too long on this than I should have, but that's okay. The neat thing is that all of this information we can find from the derivative. We don't even need to look at the graph, okay? But in previous times when we've kind of gone through this, I go straight to talking about the derivative, and we really need to kind of look and see what this looks like on the function itself, okay? So, lots of neat things there. Let's play the game right over here. So, not only the derivative, but also the second derivative can tell us all that. Okay? So, I'm going to draw, and so you might want to flip over paper, give yourself some space here. So, 3 xy axes. On the first one, we're going to sketch f of x. Then immediately below that, we're going to graph f prime of x. Then below that, f double prime. So the first derivative and the second derivative. And I'm going to draw a cubic just like before. I might make it kind of go below the x-axis, that's fine. And then, once again, we're going to do some local linear stuff. James, am I still in the frame there? Well, not me as much as this.
Yeah.
Okay. So, we're gonna draw some dots here, draw some local linearization, some tangent lines here. And at this point, it's under transitions under. All right, there's a couple of points there that we know what the slope of the tangent line is. What's that? Yeah, the zero. Well, at the horizontal tangent lines. Yeah, the relative maximum upper bend. Look at you go there, Harley. So yeah, 0 and 0. Okay. So remember how we kind of did this before with the derivative. We're going to plot those points, those slopes are going to be the y values here. Remember that, Rigel? We had kind of a discussion on that. So it's these slopes. So this is a slope of 0. I'm going to plot that as a y value, an up or down value here. And I'm going to try to draw some vertical lines just to make sure I kind of line it up. So at this point right here, if I call this A and this B, at A, I'm going to plot 0. At B, I'm going to plot 0. Now let's use our knowledge of the power rule here and of functions. This type of graph, I said, is a cubic, right? So it's something like blah, 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 x cubed, okay? What is the derivative going to look like?
Quadratic.
It's going to look quadratic. It might be like 3x squared. It's clearly not 3x squared because then that would be symmetric around the y-axis. But it's going to be like something x squared, okay? And so I know that this is going to be a parabola, either opening upward or opening downward, right? Only question is, which one is it? Well, let's go ahead and throw some numbers here, or at least think about the signs. Looking at the slopes here, are we looking at positive slopes or negative slopes?
Positive.
Positive
But
slopes.
decreasing.
Okay, and they're decreasing. So positive, so like if this would be like 10, then this might be like 1, right? So it's, and then we hit 0. So like over here we're like at 10, and it kind of comes down like that. It actually is a little bit more kind of like this. Then we hit 0. What about in this region between A and B? Negative. And it kind of reaches it gets like, it's like really negative, but then it kind of goes back to 0 right over here. So it's going to kind of like dip down. And then over here we have positive slopes again. So I'm going to do something kind of like that. Now, we kind of jumped the gun when we dealt with all of this with like position, velocity, and acceleration because I kind of wanted us to kind of deal with that before spring break. Traditionally, I'd normally do all this analysis, and then I say this is position, and this is velocity, this is acceleration. Okay, so that's okay. All of that knowledge will come into play here. So notice in the region where f of x is increasing, that was this region right here, and this region right here. What's going on with f prime?
Decreasing.
Not necessarily. Sorry. Talk to me about the values, positive or negative.
Oh, positive.
They're all positive. So increasing here corresponds to positive values here. So I'll just put POS, positive. I could put greater than 0, but that doesn't really kind of capture it as well. And where f of x is decreasing, which is this region right here from A to B, what's going on with the derivative? Is it positive or negative?
Negative.
It's negative. F of x is negative. let's talk about relative maximum and minimum. F of x has a relative max. Goes from increasing to decreasing. That's at A. What goes on with the derivative, f prime?
0.
It is 0, so you have relative max when f prime of x equals 0. Hold on, let's say this, relative max at A. So f prime of A equals 0, and f prime of x goes from positive to negative at A. So the way I write this, I'd say f prime of x goes from positive to negative at A. Of course that makes sense because we said earlier that a relative maximum occurs when the function goes from increasing to decreasing. And if increasing is when the derivative is positive, and if decreasing is when the derivative is negative, then clearly the relative maximum, which occurs when the original function goes from increasing to decreasing, corresponds to when the derivative goes from positive to negative. And if you caught all that, then good job. We said there was a relative minimum at B. So talk to me about how the derivative tells me that information. F prime of B is equal to 0, notice it does. And f prime of x goes from negative to positive at B. Awesome. So much cool stuff we're finding out. Now, I had so much fun doing that, I want to do it again. On the derivative. So let's go ahead and do some local linearization here. So draw some tangent lines here. Little local tangent lines. Mini tans. Don't really know all the values here, but there's one of them, one of those slopes of those tangent lines. I'm pretty sure I know what that value is. James?
0.
At that point?
Yeah.
Yeah, that point right there, yeah. We call that, that's kind of, actually, it's kind of, that's at C. So, down here, I was kind of vertically trying to align it here, at C, I'm going to plot this slope as a y value here on the derivative, because remember, the second derivative is the derivative of the first derivative. Let me say that again. The second derivative is the derivative of the first derivative. Okay? So I'm going to put a 0 right there. What sort of slope values are we looking at this region here? Positive, negative? They're negative. And so like this is, if this is like, I throw a negative 10, then here I'm at like, I'm almost at 0, so I'm at like negative 1, right? So it's sort of like negative 10, negative 9, negative 8, negative 7, negative 6, negative 5, negative 4, negative 8, negative 8, okay? And then over here, we've got positive slopes, okay? So that's going to be like 1, and this over here would be like 10. So we're looking at something like that, which is great because we've seen this before. And we know that if you have a quadratic, which is something like x squared, and you take the derivative of it, then you're going to get a linear function, yeah. Something like 2x, although it's not really that. But alright, that matches our expectation. What else can we say? Oh yeah, looking here, so remember how I talked about like where the tangent lines were above versus below? Yeah, look at that. The tangent lines are above everywhere where the derivative is negative, or the second derivative is negative, and the tangent lines are below here, okay? But it's more fun to talk about concavity, okay? In this region right here, we are concave down. And what do you notice about that same region on the second derivative?
It's negative.
It's negative. And then from here to here, concave up, second derivative, positive. So, on the original function, concave down like a frown, I'll put it right here, f double prime is negative. And where the original function is concave up, the second derivative is positive. And I'll put an additional note here, concave down also, with concave down, the tangent lines are above. When it's concave up like a cup, the tangent lines were below the function.
Mr. Dollar, what does that say up there?
Concave down, tangent lines above. Concave up, tangent lines below. Yep. Talk to me about that inflection point in terms of the second derivative.
Zero. The inflection point occurs when the second derivative equals 0.
Okay, so f double prime at c equals 0. And for it to be a legitimate inflection point, you've got to be going from hoo-ah to hoo-ah. You've got to be inflecting, right? So that means that that second derivative needs to go from negative to positive or positive to negative. So, and goes from negative to positive or positive to negative. I actually wasn't really thinking about designing this whole chart over here, but I'm kind of glad we did. I feel like it was kind of fun because we actually built it ourselves, you know what I mean? That's kind of a neat thing. You don't need to, there doesn't need to be something filled in every spot, but there is one more thing that we can fill in, and it's based on something that Ivan said. So this is kind of neat. Rigel, let's consider the relationship between f and f prime. Okay? So the function and its derivative. Where like it was, when this was increasing, when the function was increasing, the derivative was positive. When the function was decreasing, the derivative was negative. Now, isn't that relationship the same as the relationship between the first derivative and the second derivative?
Yes.
It is, okay. So, if I'm telling you that the second derivative is negative, what does that tell me about the first derivative in that region?
It's negative.
No, it's not negative, it's not, because over here when we saw that it was, when the derivative was negative, that didn't imply that the function above it was
decreasing.
It was decreasing. So when f double prime is negative, that tells me that
F prime
of
of
x.
x is decreasing.
Mm-hmm. And likewise, when the second derivative is positive, that tells me that
F prime of x is increasing.
f prime of x is increasing. Let's see if that is correct. When over here we've got this negative, right? So we're in negative territory. We are decreasing our values. It's going down. 0 stops, and then over here, these are positive values, and that corresponds to increasing. Pretty cool. James, that make sense? And I think that's kind of what you were hinting at earlier.
Mhm.
You're saying like the functions, talking about when this is increasing or decreasing. Okay, we're gonna start a couple problems and then probably finish setting them up. Okay. What derivative tells us? What derivatives tell us? What? Didn't see anything. All right. So instructions, please. Probably read to us those instructions.
For each column, find the open intervals where the function is increasing and decreasing.
All right. So we could probably just graph this, but why bother? We're going to use calculus and maybe almost be as fast. So we're going to do that by looking at the derivative, okay? Or by talking about the derivative. This function, if we were to sketch it, 2x squared minus 5, what does that function look like?
Parabola to the right.
Mm,
Oh no, parabola down 5.
yeah, that 5 is going to be right here, okay? And opening up or down, because that coefficient. Yeah. So it's probably going to be something kind of like that, okay? And assuming that we are, if we do happen to be symmetric here, we would expect something. Let's go ahead and see what happens. So the way we're going to do this is I want us to do this by looking at the derivative. So f prime of x is equal to 4x. Right? I want to figure out where that is positive and where that's negative. Okay? Also, it might be kind of interesting to know where it's 0. So this is sort of the process by which we're going to apply this. So I found the derivative. I'm going to set it equal to 0. Alright? When does 4x equal to 0? Well, it equals when x is equal to 0. So then we'll do this thing called a sign chart, where I've got f prime. You may remember this, we did this with velocities and stuff like that. Once again, probably should have saved that till later. That's okay. We know that at 0, the derivative is 0 here. What we want to do is we want to plug in a value over here into the derivative and plug in a value over here into the derivative. So let's plug in, like, I don't know, -2 and +2. And I've labeled this line here as f prime to kind of give us an indicator, okay? So when I plug in -2 into the derivative, I get 4 times -2, which is -8, which is a negative number. This is what's called a sign chart, SIGN, because I'm really not going to put actual numbers here. I'm just putting positive, negatives, and 0. I can put 0 here if I want to, I guess. Plug in 2 into the derivative, I get 8, which is positive. And then what I like to do is put f above that, always maintaining this sort of vertical discussion here. When the derivative is negative, I go over here to my chart, in case I forgot. F prime is negative. What does that tell me about the original function?
Decreasing.
It's decreasing. So I'll put DEC right there for decreasing. And this spot right here, where it's increasing. So, for my answer, we would say the function is increasing from 0 and then forever positive. So from 0 to infinity. So it's increasing from 0 to infinity. And we're decreasing from negative infinity all the way up to 0. And that's it.
Are we trying to find front derivative all the way till it becomes a linear?
No, we are just looking at the first derivative and kind of making some conclusions based on that.
Okay.
This one was the easiest one because it was linear and it was symmetric. I mean, we probably could have just looked at this and been like, okay, yeah, if this is the function, it's decreasing up until 0 and it's increasing after 0, right? That's what it looks like. Okay, that's problem number 1. Any questions? All right, let's go to 2. This is some sort of cubic, and it's probably shifted to the left or to the right, so this one's going to be a little bit more difficult. Alright, so same as before, let's go ahead and take the derivative. So call that derivative out to me, class.
3x squared.
You got 3x squared,
Minus 4x.
minus 4x. I'm interested in those critical points, specifically where it equals 0. So I'm going to set that equal to 0 and kick into algebra 2 mode. I've got a quadratic, I want to solve it. I've got lots of tools, quadratic formula, graphing, factoring. Factoring is going to help us out here. I'm going to factor out an x. And I end up with 3x minus 4. So I have x times 3x minus 4 equals 0. So that indicates that either x equals 0 or 3x minus 4 equals 0. Solving for this, I have x equals 4/3. So just to be clear, those are the two locations where the derivative equals 0. F prime 0 and 4/3, which I'm going to write it as 1.33. Those are the two locations where the derivative equals 0. What I'm going to do is I'm going to plug in a value here, I'm going to plug in a value here, and I'm going to plug in a value here, figure out if it's positive or negative. That will then inform me whether the function is increasing or decreasing on those regions. Okay? You're welcome to work on this and the next couple problems. They're all very similar. We'll finish wrapping this up on Monday, doing these problems, and then I'll sign the whole thing for homework on Tuesday. Okay? So then we talk about functions, derivatives, what they tell us. They tell us whether it's increasing, decreasing, inflection points, concavity. Oh my gosh, inflection. Rows and backs, rows and min. Okay? Lots of good stuff to think about over the weekend. See you then.